Welcome to today's Explainer. I am so incredibly pumped to dive into this one with you. Today, we're basically decoding the invisible nervous system that powers our entire modern world, the electrical grid. And more importantly, we're looking at the massive revolutionary upgrade it is undergoing right now. We're going to trace the path of electricity from a single, tiny piece of hardware monitoring a local transformer all the way up to the macro level, where these huge, intelligent networks are literally laying the foundation for the smart cities of tomorrow. So if you've ever wondered how your house might soon talk directly to the power grid, or how we can prevent those massive cascading blackouts before they even start, well, you're in the right place. Let's get right into it.
But to really understand where we're going, we kind of need to face the reality of where we are right now. And that begs a pretty big question. What actually happens when our aging, completely overloaded power grid finally gives out? Think of the traditional distribution transformer. You know, that big gray metal cylinder hanging up on the utility pole in your neighborhood? Think of it like an aging, overworked patient with dangerously high blood pressure. Its job is to step down high voltage electricity so it's safe for your house, but it operates under immense stress. We're talking constant overloading, harsh weather, and severe overheating. And the crazy part? Traditionally, utility companies only find out this patient is sick when it completely flatlines. That means fatal blackouts, fried equipment, and just huge disruptions to our lives. Because up until now, maintaining these things has relied on periodic, manual inspections. By the time a human inspector actually spots a problem, it's usually way too late.
So, the cure for this failing system? It requires a complete paradigm shift. We have to completely ditch the old, centralized grid. That old model was basically a blind, one-way street. Power just flowed passively from some massive power plant miles away straight down to you, the consumer. And utilities just crossed their fingers and relied on those manual checks to see if things were still working. The new paradigm, though, is the smart grid. This thing is multi-directional, highly active, and most importantly, it relies on real-time, 24/7 monitoring. The smart grid doesn't just dumbly deliver power, it constantly communicates. It gathers massive amounts of data, and it literally adjusts itself on the fly. It takes this rigid, top-down piece of infrastructure and turns it into a living, breathing ecosystem.
Okay, so how do we actually build this intelligence into the grid? Let's start at the micro level to see how we cure those failing transformers. It all kicks off with the Internet of Things, or IoT. Step 1, we take physical IoT sensors and attach them right onto the transformer to constantly measure its vital signs. We're talking voltage, current, temperature, the works. Step 2, an ESP32 microcontroller, which is basically a tiny, highly efficient computer, processes all that raw health data right there on the spot. And finally, step 3, it instantly transmits that data wirelessly to a cloud interface, like the Blink IoT platform. And just like that, suddenly that blind, silent piece of metal on a pole is speaking to us in real time. It's giving operators a second-by-second health update from miles away. It's honestly a game changer.
Now for the hardware folks out there, let's look at the specific components doing the heavy lifting here. This setup is effectively the grid's brand new nervous system. We have the ZMP101B sensor, which acts kind of like an EKG, precisely tracking the voltage characteristics. Then there's the ACS712, which tracks the actual current flow. And crucially, we have the DS18B20 temperature sensor. This acts as a highly sensitive thermometer for the transformer's oil and internal body. Because look, if that oil gets too hot, the insulation breaks down and the transformer literally blows up. Using this highly accurate, incredibly low-cost hardware setup is exactly what makes widespread, real-time monitoring actually possible without, completely breaking the bank. And when all this data hits the operator's dashboard, the difference between a healthy system and an absolute crisis is undeniable. You can clearly see a healthy state. The voltage and current levels hold steady, doing exactly what they're designed to do. But contrast that with a phase failure, a no power state. There is this immediate, dramatic drop in the metrics, followed by these wild, erratic fluctuations as the system desperately tries to reconnect, before just dropping completely to zero. Because the smart system spots this drop the exact millisecond it happens, it can immediately trigger a relay to protect the rest of the equipment on the line. This is real-time proof of how predictive analytics act as preventative medicine. It stops a local fault dead in its tracks before it cascades into a total system blackout.
This hard data fundamentally changes the game for maintenance crews. It translates raw vital signs into actionable intelligence. For instance, state 0 is normal. The system is okay. Oil temperature is sitting at a very comfortable 25 degrees Celsius. But jump down to state 4, an earth fault, immediately the voltage partially drops and you see these sudden dangerous current spikes. Or think about the temperature trigger. If the oil hits 52 degrees Celsius, the system instantly throws a high temperature error. The operator doesn't have to guess or wait for a phone call from an angry neighborhood. They know exactly what the problem is and exactly where it's happening. This completely shifts the entire utility industry from reactive maintenance, waiting to fix things after they literally explode, to proactive maintenance. And that saves an unbelievable amount of money and downtime.
Zooming out a bit though, these microcontrollers on the transformers actually need a reliable way to talk to the broader utility network. We've mentioned wireless IoT transmission to cloud platforms like the Blink app. And for larger data streams, utilities absolutely use 5G networks and optical fiber. But actually, one of the most brilliant methods being used is power line communication, or PLC. This is so clever. It uses the actual existing power distribution cables themselves to send the digital management and control signals. It's incredibly efficient because, well, the infrastructure's already there. It ensures remote monitoring can reach even the most isolated rural parts of the grid without utilities having to go out and lay miles of brand new communication lines. So let's look at how these micro-level upgrades trigger a massive macro-level evolution. Historically, we had that one-way flow from a centralized power plant to the consumer. But by outfitting the grid with these smart IoT sensors, we completely transform that rigid infrastructure into a highly flexible, complex network. This new grid is multi-directional, and that is absolutely vital because it's the only way we can seamlessly integrate distributed renewable energy sources. Think about it. Wind and solar are totally decentralized, and their power output fluctuates wildly depending on if the sun is shining or the wind is blowing. A smart grid uses real-time data to balance all these varied, unpredictable inputs perfectly. And this incredibly interconnected grid gives rise to an entirely new concept, the prosumer. In the old grid, you were just a consumer, right? You flipped a switch and power just magically arrived. But now, you are no longer just passively taking electricity. A prosumer actively produces energy, maybe through those solar panels on your roof, stores it in home batteries, and then intelligently exchanges it with the smart grid. So if your panels are generating excess power during a bright sunny afternoon, the smart grid allows you to sell that power right back to the network. You actually become an active participant in energy management, which, by the way, dramatically reduces your personal costs and lowers the carbon footprint of the entire system. Because of this constant bi-directional communication between the prosumer and the utility, the network can intelligently balance loads on demand. These digital technologies enable what we call active demand management and peak shaving. Peak shaving is such a cool concept. It's where the smart grid automatically smooths out massive spikes in energy demand. Like, that dreaded moment in mid-July when absolutely everyone gets home from work at 5 p.m. and cranks their AC at the exact same time. By slightly, almost unnoticeably adjusting smart thermostats or drawing on stored home battery power during those intense peaks, the grid avoids overloading. This results in incredibly high energy efficiency, massive cost savings, and a grid that is vastly more stable. Ultimately, these smart grids become the very foundation of future smart cities. When every single building, transformer, and renewable energy source is communicating, we achieve truly intelligent access to energy. The system knows exactly where power is needed at any given second, and exactly where it is being wasted, and routes electricity with unbelievable precision. This interconnectedness not only eliminates massive amounts of waste, but it also allows us to extend highly reliable services to previously underserved areas. It is the necessary, fundamental technological bedrock required for electric vehicle charging networks, automated smart buildings, and truly sustainable urban living, the whole shebang.
To really wrap your head around the sheer scale and importance of this transition, listen to how energy analyst Jesse Burst puts it. He compares intelligent meters, the very devices enabling this two-way communication, to the invention of the telephone system, the transcontinental railway, and the internet itself. And honestly, that is not an exaggeration. Just as the internet completely decentralized information and revolutionized how we communicate, the smart grid is decentralizing power. It is fundamentally revolutionizing how we produce, consume, and share the very energy that keeps our modern world turning.
And that brings us to the end of our explainer for today. We've gone all the way from a tiny, inexpensive IoT sensor monitoring the oil temperature of a local neighborhood transformer up to the sprawling, hyper-intelligent networks that will literally define our future cities. I want to leave you with this final, provocative thought. The grid of the future isn't just some abstract piece of infrastructure that happens to you. It requires your active participation. As you become a vital node in this massive smart grid, a true prosumer, are you ready to actively power the city of tomorrow? Thank you so much for joining me today, and as always, keep learning.